Right, thank you, Petra. So this is a little ongoing project with my co-author. It's titled Fast and Efficient Data Science Techniques for COVID-19 Group Testing. So we're by no means health experts or biologists, but we're approaching this problem from a statistical viewpoint. Right, so there's been a lot of interest in group testing. So here's an excerpt from New York Times article. It says 5 people, 1 test. This is how you get there. What this is referring to is actually Dorfman technique. This is actually also an economist. Yeah, I forgot to mention we're from the economics department. So what he decided to do, Dorfman, almost 8 years ago, was so suppose these are 100 people. So the red ones are infected ones, and then you group them into. So this is going to be the first group. So 5 individuals in the first group, 5 individuals in the second group, and so on. And then you, instead of testing every single one of them, you test groups. So the idea is really trivial. So in the first stage, you're going to test those groups, so this first group, second group, and then in the second stage, so this group is going to be positive because there's an infected individual, and this group is also going to be positive. And then inside those groups, you're going to test each one, okay? And then you're going to discover this individual, and you're going to discover this individual. So in the first stage, you're going to take, this is going to take about, no, not about, this is going to take exactly 6 tests. So 1, 2, 3, 4, 5, 6. And then in the second stage, this is going to take 10 tests. So while you have 3 individuals and 2 are infected, you're going to need only 16 tests. So almost 50% reduction in the number of tests to detect infected individuals. But you can see if, for example, the infection rate was 1%. Sorry, if it was just one infected individual, then you might have needed less tests. Or if it was, for example, 0 individuals, then you'd need just 6 tests. There's been an improvement over this trivial method. There was a note by Sterrett and then other works. For example, this one, the improvement is in the second stage. You don't need to do everyone individually if the disease prevalence rate is small. Petra, can you hear me? Okay, thanks. If the disease prevalence rate is small, then we can test this guy, and then once you discover someone who's infected, then you can group the remaining ones and do the groups. So again, also a trivial improvement. Now you probably see the gains from doing group testing already, but FDA really summarized the benefits in this statement. Because samples are pulled together, ultimately fewer tests are run overall, meaning fewer testing supplies are used, and results can be returned to patients more quickly in most cases. So just to summarize, when you do group testing, this may lead to increased testing throughput, limited use of chemical reagents, and higher because your test can test more people. This is going to allow to cover more individuals overall. When people mention group testing, the big concern that arises is the dilution, the question of dilution. And there's been studies, I list here just a few very recent studies that show that dilution may not be such big of a problem, allowing group testing benefits to persist. So, for example, in this study, which I'll mention in a little bit later, they merged samples of up to 64, and they were still able to detect infected individuals. In this study, it was even 100 individuals, and they were still able to detect. So for the group testing was also used for HIV and influenza in the past, and malaria. Actually, this study by Dorfman that I showed you, this was used for screening out syphilis for people who were drafted by selective service. And this all is completely legal by now. So there was an FDA's emergency use authorization, which authorized so-called sample pooling, which is the same as group testing. They say this is going to be sample pooling becomes especially important as infection rates decline and we begin testing larger proportions of population. Interestingly, they don't require the correspondence of the pooling test performance as opposed to individual test performance to be 100 ppA. So it doesn't have to be as good as if you test it individually. So I want to differentiate between adaptive and non-adaptive techniques. The one that I mentioned by Dorfman, it's adaptive in the sense that, so adaptive is, there's another word for that is hierarchical, in a sense that there's several stages. In Dorfman's case, there were 2 stages. And in the second stage, you adapt to what you saw in the first stage. There's the main characteristics of adaptive groups testing are, so these 2 are mentioned. And then so in the second stage, I need to know what happened in the first stage before I can proceed. In non-adaptive group testing, so non-adaptive group testing, these features are flipped. So instead of several stages, we have just 1 stage, and we have overlapping groups. So in Dorfman, everyone participated, every individual participated in every group once. In non-adaptive, I can have overlap. So one individual may participate in one group and then in some other group. So we're going to be focusing on non-adaptive techniques, not as old as Dorfman. Actually, I won't consider Dorfman because it's outdated. Fresher non-adaptive techniques, and we're going to propose a method that's based on L1 norm sparse recovery that works pretty well. So before I go into details, so this has been mentioned, the RT-qPCR procedure. I want to just point out something here. In a few words, what this does, this is a detection technique for COVID-19, not specifically for COVID, but can be used for COVID. What this does, this takes the virus DNA and it amplifies it exponentially through the process of heating and cooling up to 40 cycles. And then there's a fluorescence signal associated with it. And if it crosses some threshold before 40 cycles, if it crosses it before, then we declare this patient positive. So we can use this information, this cycle threshold information. When did this fluorescent signal cross the threshold? So when did this happen? To help us with the group testing. So we can use this quantitative information. You can go to this. I can either scan with your with QR scanner or use this link to see a video about RT-qPCR. This is what you can see from RT-qPCR. We see, for example, this one, the red one. It shows the trajectory of the fluorescence signal for one individual. Okay, so the signal in one positive individual. So the signal at approximately cycle number, so whatever this is, 29, it exceeded the threshold, and so qPCR tells us that cycle CT, the cycle number was 29. And because it's low, it's lower than 40. Or whatever threshold is here, we declare this patient positive. But if you dilute with, for example, 1, you're just gonna have to wait a little bit more. Okay, if you dilute with 3, you have to wait a little bit more. And if you dilute with too much, and so in this study, if you dilute with 63, you may not be able to observe it. Okay, so let me formulate the problem. This is I threw out a lot of math, but just as simple as it can be. We have n individuals, and k of them are positive. And we want to use m test, and m is small order of n, so a lot smaller than n, to detect those k individuals. So we want to design this pooling matrix. One of the steps is that we want to design the pooling matrix that will put every individual. So here we have individuals. These columns are individuals, and here we're going to have values, 0, 1 values, which puts every individual in some group. So here, for example, if this value is 1, that means first individual is going to get allocated to group number 1. This is going to be vector x, which just tells us whether so vector of this is 0, 1s. It could be a vector of 0, 1s, which tells us who's infected. So which individuals, it's n by 1 vector, which individuals are infected. But X could be, importantly, X could be these readouts from qPCR, so these cycle thresholds. So there could be very many different models. The simplest one could be to just say that, so we observe this Y, observe the results of tests. We don't observe how every individual tested, but we observe the results of group tests, and then there might be some noise. But the goal is we want to infer X. We want to find whoever is, so that's the ultimate goal. We want to find, using M, which is small number of tests, we want to find who's infected. So there's going to be two challenges here. One is how exactly do we design the pooling matrix A in this non-adaptive setting? And the other is how do we decode once we design this A, how do we decode and observe Y? How do we decode this and retrieve X? So for the first question about designing the pooling matrix, we're using this constant column weight design. This has been in a different branch and not related to sparse recovery. This has been suggested, and it worked well. The idea is that so in each column, we're going to select some number L of ones, and we're going to bootstrap them in each column. So for example, here L could be equal to 3, and you could have up to three ones. Okay, so here you could have 2, but the maximum of 3. So the benefits of this design is that you want to have this L not so big, so that one sample is not divided into too much, so we avoid dilution. Empirically, this also led to, in their experiments, which are based on different techniques, led to better performance, and this also leads to better performance for us, as opposed to if you use, suppose, just Bernoulli. And there is this could be theoretically justified. So
you have 5 minutes. Sorry.
Okay, thank you. Okay, I don't want to present too much math here, but what I want to say, if you design A this way, and we're showing it, A is going to satisfy so-called restricted isometry property, and you'll see. So let me actually skip this. So this is what we show, but you'll see why this is important. So this will show up on this slide. So I said first step is we design how to pool people, how to do a matrix A, and then second step I said was to infer X. And then, so how do we infer X once we pooled everyone and observed the results? How do we infer now X? From first principles, what we want to do, we want to find this L0 norm. Basically, what this means, we want to find the smallest number of infected people. We know that there's not going to be too many people. So we want to find this smallest number, subject to this restriction, which is just AX equals to Y, and then there is some noise. So subject to what we observe, essentially. And then it is known that this is a non-convex problem, and this could be translated, if you just put L1 here, this could be translated to a convex solvable, not NP-hard problem. The only thing that's needed to guarantee that solutions are close is that A is RIP, so restricted isometry, and that's what was shown in the previous slide. This problem also goes under different names in compressed sensing, electrical engineering literature, signal processing literature. This has the name of basis pursuit denoising, but for statisticians, this is more known as lasso. So it's as simple as just doing lasso with a few tricks, but main one would be just to add also a non-negativity constraint, because we know X could not be negative. So very briefly, what are the benefits? This approach is one stage, it's non-adaptive. The number of tests we're gonna need is, so if the number of tests you're gonna need if you do individually is gonna be exactly n, because you're testing everybody. But here we're gonna need this order. So if K is small, and K is generally going to be small, so we're operating in low disease prevalence, there's very few infected individuals, and this is gonna go log n. So a lot less than just n. These lasso estimates are also gonna allow us to reconstruct this CT signal. Okay, CT is not exactly the same as viral loads, but there is some correlation going on. So we're going to be able to reconstruct also some information and not lose it. And this also works. This approach also works well if you have noise. So this is just a simple illustration. I'm gonna put a link. It's gonna be provided later on, how you can play with this kind of this simulation kind of exercises. So what I have here is I have 100 individuals. So I say here, I have 100 individuals, 2 are infected, so 2 are positive in reality, and then I use only 20 tests. And then this is the true vector. So this was generated randomly. So this individual is infected and this individual is infected. And then these are the current techniques. I obviously don't have time to go over them, but they're kind of known. You can also see them on Wikipedia. And this is the proposed one. So you can do many experiments like this, but in this particular example, you see that it's recovered the truth. So if you repeat this over many times and do average over 200 Monte Carlos, if you do and if you plot the RMSE, so the true vector X versus what is predicted by the method. So if you plot RMSEs for different methods, and this is our method, then essentially at 20 tests are enough to reach the zero error. Okay, 20 tests are enough compared to others. You can also do all kinds of. Yes, thank you. So you can also do all kinds of sensitivity, specificity. So all of this will be is in the link. Also ROC, things like that. So you can either scan this or go to this link, and this will take you to Colab, where you can immediately play with it. And we're still working on this. Once the project is over, we're gonna put everything on GitHub. Okay, so I'm running out of time. There's people realize that this approach works well. There's similar studies. This is actually a very big study from India. So TLDR, main things, group testing can be beneficial at low prevalence rates, and no one believes the prevalence rate of COVID is going to be too big at any single point of time. L1 recovery works and is theoretically justified. Everything is fast and efficient. So by fast, I may refer to the fact that it's one step, it's non-adaptive. If you're interested in this, you can contact me. There's also Chris Builder is probably the leading researcher from Nebraska who works on group testing. There's also a book and there's also references. So So we're small. It's just me and my co-author. So feel free to contact us if you want to. All right. Thank you.